Hi, everyone. Thank you for attending my virtual presentation. Today, it's my pleasure to present our work on maker-friendly chemical-based sensors called EcoPatches. This work came from an internship I did at Microsoft Research. At the time, I was finishing a PhD at the University of Washington, but I'll be starting a faculty position at the University of Toronto this fall. So in this project, we're interested in tackling the problem of overexposure to ultraviolet or UV radiation, which has been called the most prominent and ubiquitous physical carcinogen in our natural environment. We are so accustomed to sunlight that we often forget that it's affecting us unless we're in extreme conditions. In fact, many people often internalize this notion that people in stereotypically sunnier places are at a higher risk of skin damage. But it turns out that at least in the United States, it's not necessarily the people in California, Florida, or Texas that have the highest rates of skin cancer, but sometimes it's people in cloudy places like Washington and Minnesota. This is partly because cloud cover gives people a false sense of security about their skin. To help people understand how much UV radiation is around them, there are hardware devices like handheld meters and smartwatches. Although these get the job done, they require explicit actions from the user in order to retrieve a measurement. And in most cases, they also require battery power, which limits their usage. To address these issues, some companies have begun to produce disposable chemical patches that change their color as they're exposed to UV light. While these address the limitations of hardware devices, we see two shortcomings with them. First, they have a fixed formulation and design, which means that there isn't a single patch design that is going to make everyone happy. And second, it's hard to find a design that is both precise and easy to read. In light of these limitations, we set out to create EcoPatches, which are disposable inkjet-printable chemical sensor patches that show their cumulative UV exposure over a single day. EcoPatches address these three design goals of formulation flexibility, aesthetic flexibility, and interpretability in a couple of different ways. First, we created a process of making EcoPatches that we believe most makers can do on their own, using an inkjet printer and chemicals that can be purchased online. This way, people can create their own EcoPatches that suit their own skin sensitivities and aesthetic taste. And second, while we try to provide as much design flexibility as possible, we came up with specific recommendations that people should follow when they create their own EcoPatches to maximize interpretability by both humans and an algorithm. Now, before I go into how an EcoPatch works or how it's made, I first want to provide a little background on how UV exposure works. The amount of UV in a person's vicinity depends on factors like the ozone, cloud cover, and the time of day. The measurement that is most relevant to skin damage is cumulative UV exposure, which is the integral of instantaneous exposure over time, measured in a unit called UVI hours. The amount of exposure a person's skin can sustain before damage depends primarily on their melanin production. On the right, you can see the Fitzpatrick scale, which is a standardized scale describing skin tones. Because these ranges don't have much overlap between them, it's hard for one product to really satisfy all skin tones. With that in mind, let me describe the foundation of an EcoPatch, which is its UV-sensitive ink. The ink's two main components are a photoacid generator and a pH indicator. When these components are exposed to sunlight, the photoacid generator produces hydrogen ions that increase the acidity of the pH indicator, which thereby changes its color. The solution also includes a basic buffer to ensure that this reaction doesn't happen too quickly, and ethanol to make the ink more viscous to the point where it flows like normal printer ink. Something important I want to note about this reaction is the fact that pH operates under a logarithmic scale. This means that EcoPatches exhibit a nonlinear color change as they are exposed to more UV radiation. In this photo of evenly spaced EcoPatches, you can see that there's a significant color change when they are first exposed to UV radiation. But as they get to higher exposure levels, the color change is more subtle. In the end, the dynamic range and rate of change for EcoPatches depends on the ratio of the solution's components. We use this ink in a three-step fabrication process involving an inkjet printer. In the first step, the maker uses both their UV-sensitive ink and regular inks to print their design on a sheet of temporary tattoo paper. And we pick temporary tattoo paper because it is pH neutral and thick enough to keep it separate from the skin. Once the inks are done, the maker then applies a thin layer of archival resin, which provides waterproofing and chemical encapsulation while slowing down the chemical process. Finally, the maker can apply skin-safe adhesives to the back of their EcoPatches so that they can be worn. There are practically an infinite number of ways an EcoPatch can be designed, so we set out to provide some guidelines to ensure that EcoPatch is still interpretable. I don't have enough time to cover the survey that we conducted to elicit these guidelines, but I've highlighted the main takeaways here. First, design should minimize the distance between dynamic and static regions to facilitate comparisons. Second, design should align the spatial arrangement of the static regions with visual metaphors. Third, design should also align the color changes of the dynamic regions with visual metaphors. Fourth, design should avoid functional attributes that disrupt aesthetics. And fifth, design should include color references that correspond to meaningful values, even if those values are on a nonlinear scale. Taking these design principles to heart, this is the EcoPatch design that we created for our specific evaluations. Along the bottom, we have a reference color scale where each part corresponds to a specific threshold along the Fitzpatrick scale. And at the top, we have a UV-sensitive region that is contiguous to each level of the scale. Now, people can interpret an EcoPatch by doing a side-by-side color comparison between the two halves of this particular design. But the color scale also allowed us to use computer vision to interpret the ink's color for the user while accounting for ambient lighting conditions. The first step of this pipeline involves using template matching to identify the different regions of the design. We use a dense SIF feature extractor and brute force matching to do the template matching. Once we know where the different regions are, we could summarize their color in the HLS color space using a vector median. We then train a k-nearest neighbor classifier using the colors along the reference scale and their known UV exposure values. We then test the UV sensitive region against that model to produce an exposure estimate. To demonstrate that we satisfied our third design goal of human and machine interpretability, we conducted a pair of studies. First, we exposed 11 EcoPatches to increasing amounts of natural UV radiation, going from 0 to 11 UVI hours. To evaluate the human interpretability of these patches, we had 35 participants read each EcoPatch on its own in a randomized order. And to evaluate machine interpretability, we took photos of each EcoPatch in 10 different locations and analyzed them automatically using the pipeline I just described. This graph shows how well the user's readings along the vertical axis align with the actual exposure levels along the horizontal axis. The diagonal indicates the ideal case where people estimate the EcoPatch values accurately. The Pearson correlation coefficient between the readings is 0.79 in this case, which is reasonable but not strong. Although the bars generally overlap the diagonal, some of the bars are quite wide, which indicates that different people see the same color in very different ways. When we look at the corresponding graph using our pipeline, we can see that the error bars are much tighter. This manifests in a stronger Pearson correlation coefficient of 0.9. You notice that the correlation graph deviates from the diagonal at higher exposure levels, and this is due to the logarithmic nature of the underlying chemical process. There are many challenges and opportunities for future work we encounter during this project. One of those opportunities has to do with the fabrication methods. We try to use our ink in methods other than inkjet printing. For example, we tried screen printing, but found that it wasn't really amenable to rapid prototyping, since each revision required a new screen. We also considered lamination as an alternative technique, but felt that the equipment required for it would be too sophisticated for an average maker. We also try to use our ink in form factors other than chemical sensor patches. One of our more eye-catching ideas has been color-changing hair. The UV-sensitive ink we created can be easily repurposed into a hair dye or a mousse. We hope that people will take our ink formulation and try out other form factors on their own in the future. So to conclude, I'd like to thank the awesome research team that made this research possible, and I'd also like to thank you for listening to this talk.